Okay, so this is the last class. So what I'm going to try to do today is cover a lot of material very superficially, just to give you a glimpse of what we could do if this class was twice as long. And I had the opportunity to go into depth and really teach you how to have a mastery of this subject. So last time, the big punchline of last lecture was that noise stabilizes patterns. And or at least we saw that in the case of patterns in time, which is what I'm calling a population cycle in say an ecological system made of predator and prey. So we saw that noise stabilizes those things, and uh, and in fact, what that means is that if you don't take into account the discreteness of populations, you do not have a well-principled description of population oscillations. It's an essential part of it, and it's related to fundamental issues in modeling, I would say, where stochasticity becomes an intrinsic part of the description. So this is very paralleling what happens in quantum mechanics and high energy physics and quantum field theory, where classical theories have certain symmetries with them, but when you look at the quantum theory, those symmetries are broken by anomalies. So this is the topic of an alternative to, well, not alternative, another aspect, if you like, of spontaneous symmetry breaking related to things called generalized symmetries and all sorts of things like this. So I'm not going to go into anomalies, but what I want to do today is I want to talk about the spatial version of that. And this is something that we started at the end of last lecture. So at the end of last lecture, I introduced for you a model of what's called a Turing pattern. So what we looked at was a predator and prey that are allowed to move around in space. But the predator and prey have certain properties that are greater than what we talked about with predator prey. So I'm going to call them activator in this case. So the activator catalyzes its own production and catalyzes the production of the inhibitor, whereas the inhibitor reduces its own concentration and that of the activator. And these were first realized in the context of, say, chemical pattern formation and so on, but we're now applying these in an ecological context. And then what I did was I gave you a series of cartoon descriptions of saying what would happen if I had some spatial heterogeneity in the system, how would it respond? And I argued through the cartoon pictures and showed you that in the end, what would happen is that you would end up with patches of prey surrounded by predators. And so you would get patchy pattern formation in the system just by arguing based on sort of cartoon pictures. So today, what I want to do is put that into mathematical perspective. So I'm going to show you now a model called the Levin-Siegel model for herbivore plankton interactions. So this is meant to answer a question, which is when you look at the distribution of plankton in the ocean, what you find is that they are patchy. And the question is, well, what causes that patchiness? And back in the 1970s, Lee Siegel and Simon Levin is now one of the most famous theoretical ecologists in the world, if not the most famous and most decorated. Friend of mine, just an amazing influence on ecology. This is one of the classic papers that they did in the 1970s, one of the very first theoretical examples of Turing instabilities, and I'm going to show you that. We're going to look at the effect of extrinsic noise on the Turing patterns that you get for these patchy herbivore plankton interactions. And then I'm going to show you that what happens when we make an individual level model for this. I'm going to do this very quickly. I'm going to scoot over the deterministic part because it's basically stuff that you've already seen, just done for a slightly different differential equation. And then I'm going to show you that in order to model that, we have to use ideas from quantum field theory. So I'm going to show you those very quickly, show you how to do the Van Kampen expansion that we already did last time, and then end up by showing you the dramatic consequence for a pattern formation. Okay, well, I remember this is the last lecture. So pass these around. So I always give out chocolates in the last lecture. So just help yourself to as much chocolate as you want, because you might need it. You might need the chocolate to stay awake during the more technical parts of the talk. Okay, so let's get started. So so let me introduce the Levin-Siegel model. So the idea is that we have plankton, and they are the prey, but they're prey with the activator function B, and the herbivore is the predator. So that we'll call the inhibitor, and that we will denote by the symbol A. And in the context of these models, what does activation really mean? So activation in this particular case means that obviously having the prey is an incentive for the predators. Pass behind you. Okay. Having the prey present then acts as a place where predators will naturally want to go and exist. So but there's another factor of activation, is that you also have to activate yourself. So activation, the prey activation, what is that? And that is something called the Ali effect, named after Mr. Ali. And what this is the higher reproduction rate at higher density.
Pedro, you didn't share your screen?
I did.
Really?
Yeah, I did, yes. It didn't work. Okay,
yeah,
let's try
it's
it
not
again.
like on Zoom.
I did it before you joined. Let's try it again. It had one of those blips. Thanks for letting me know. All right. Okay. So you can see the screen and it's still recording, right?
Yeah, still recording.
Okay. So here's my screen.
Yeah. That's okay now.
So you didn't miss much, but you heard everything I said, right?
Yeah, right.
Perfect. Okay. Did you get any chocolate?
Yeah. Thank you.
You're missing the best lecture to be here in person. Okay. So prey activation means the Ali effect, which is a high reproduction rate at high density. So anybody, so this is just an empirical fact. Anybody who's ever had a long distance relationship can understand how this might happen. So what we're going to see is that there's going to be an extra nonlinearity in the problem due to this. So let's write down the equations of motion. So the equation of motion for A is some diffusion coefficient, and then predation. So just as we had before, and then we have death, but we're going to include death in a nonlinear way. So we're going to include it as A squared. So what does A squared mean? So if the death term just goes like A, that just means that the predator just dies, exponentially decays. If it goes as A squared, it means it's a cooperative phenomenon. In other words, basically what happens is the predators compete and attack and kill each other. So this is predator competition. And if you want to see an example of that, I encourage you to look at today's news, this afternoon's news. I'm not going to say anything more about it, okay? All right, so that's the equation for the predator. Now for the prey, so now we have dB by dt. So again, we have a diffusion term. And then we have the birth rate, as we've had before. Then we're going to have a nonlinear birth rate. So it's going to go as EB squared like so. And then there is a P AB, the usual predation. and there can also be higher order terms as well. So I'll put this in as a sort of optional term. I'm not really going to talk about it, but there can be other terms which are required in order to have coexistence stability. So this term over here is the Lee effect term. This is the enhancement of the birth rate when there's a higher density, and the two terms that are specific now to these Turing type phenomena are these two terms over here like that. So then you can go and work out the theory, and I'm not going to go ahead and do it because it's straightforward. It's not at all trivial. You have to do some calculation, but what you find is that you can have a steady state of predator-prey coexistence. And the conditions for that are that P is greater than E, and P squared is greater than DE. And the fixed point that you get for this is B star equals B D over P squared minus DE, and A star equals B P over P squared minus DE. Hopefully I've copied those down right. So you find the coexistence just as we had before, steady state. Then you do a linear stability analysis. And what you find is that the condition for pattern formation, and again, I'm skipping all the calculation. It's fairly standard. It's in many textbooks, and it's exactly what we've talked about a couple of weeks ago. So you just do the stability analysis, look for the real part of the growth rate, and so on. And what you find is that condition for pattern formation is this condition over here. I'm going to write it down. It can be written down in this way: dA over dB is greater than P over D minus the square root of P over D minus E over P, and then this quantity to the minus 2. And so that's the formula that you get. And if we typical values for these quantities, things like this: B might be half, C is a half, D is a half, P is 1, something like that, just coefficients of order unity in the appropriate units. And that requires then that D over A over DB has to be greater than 28. Okay, so that's the condition, just like the Rayleigh condition that we worked out for convection. So what this says is that these predator and prey, we talked last time about the fact that the predator have to be able to move around very quickly and essentially box in the prey, and that's the mechanism responsible for the pattern formation. But now we see that for this to actually form a pattern, you have to have this huge disparity in their diffusion coefficients, and this condition is virtually never satisfied. And the reason is very simple. You know, if you're looking at, say, how pattern forms, say in spots on a leopard or something like that, you're looking at some molecules diffusing. They all have more or less the same diffusion coefficient. They're all just molecules of the same size. They're all diffusing through the same sort of membrane. So these diffusion coefficients do not differ by orders of magnitude. And so this is why this is never satisfied in nature. And that means why that it was very hard to find or to find or create documented versions. So this was sort of kind of a sort of minor scandal, as it were, in pattern formation, that everybody believed that Turing patterns were a fundamental mechanism, but nobody could actually point to one that's real. And every now and then somebody will find an example of a mechanism where you actually, for various reasons, you can really show it's a Turing pattern. And if you can do that, those papers get published in Nature. And there's maybe a very small handful of them. Most of the papers are artificially created systems, if you like, analog computers for a differential equation. Okay, so then let's ask ourselves the following question. Okay, that's fine. So now let's ask, what about noise? So let's first of all look at the effect of extrinsic noise. On the idealized dynamics in this coexistence region. So here is our strategy for doing this calculation. I'm going to do the extrinsic noise version first, because once I've shown you that, it's very easy to then work out what happened for the intrinsic noise, the discreteness, because we know that it's more or less the same formula, but now that we have to take into account the multiplicative noise. So what is our strategy going to be? Our strategy is going to be, eventually, we're going to use the Van Kampen expansion. What we know is we get a Langevin equation with additive noise and but the coefficient of the noise is the mean density from the previous order and perturbation theory. So that's how multiplicative noise is represented in the Van Kampen expansion. So that's going to be how we're going to solve this problem. So I'm going to show you how we write down the Langevin equation first. Now then the next question you might want to ask is then I'm going to show you that this this creates a dramatic change in the phase diagram. With experimentally testable predictions. Okay, so let's just show you the general principle of how you do the calculation here. So here's the basic idea. So the basic idea is we're going to look for the fixed point, take the fixed point, the one that I told you about just a few minutes ago, take that fixed point, and then linearize around it and add noise. So then what you're going to get, if I have some variable x, multi-dimensional variable x with some degrees of freedom, you're going to get an equation with a structure that looks like this, x plus gamma. And in this equation, gamma is going to be 0, and expectation value of gamma of r and t gamma of r prime t prime is going to be some sigma squared times delta of r minus r prime delta of t minus t prime. So if I linearize the equation, differentiate it, take a Fourier transform in space and time, it's going to have this kind of structure. So let's just tell you what the variables are. So when I write it like this, what I mean is this: the vector x is a minus a star, and the vector b is b minus b star. So this is the vector is the deviation from the equilibrium coexistence points. The matrix A that includes spatial derivatives. So this vector here is really going to be a Fourier transform vector. So x hat is going to be in terms of frequency and k. So we're going to Fourier transform in space. We're going to Fourier transform in time. And if I write down what the matrix A looks like, you can work it out, and it looks like this. So that's the matrix A, and again, there's nothing tricky in reproducing this calculation. So you find that. And now the thing that we want to compute is the order correlation function of the fluctuations. So we want to compute the power spectrum of x. So that is the following. So we're going to compute P of k and omega, and that's going to equal the expectation value of x as a function of k and omega, absolute value squared, like that. So that's the thing that we measure. And just what we did last time was we looked only at population cycles in a spatially uniform system. So we didn't have k, we just had omega. And then we saw that the frequency of oscillation showed up as a peak in the power spectrum. So whenever you see a peak in the power spectrum, that tells you about a natural resonant frequency. So we calculated that. The same thing is true here. So what we'll now look at is peaks in the power spectrum, both as a function of k and omega, and that's going to be the readout for the formation of patterns. So what we will read out is that peaks in the power spectrum corresponds to emergent patterns, population cycles, and in some cases, traveling waves. So that's the readout. So let me then tell you what the formula is. So then we go ahead and do the calculation. And what you find is that P of k and omega is, this is fairly disgusting. I'll just copy it down so you can see that we actually can do the calculation. And then the denominator is really quite long. P, B, B star plus D, A, D, B, k to the fourth minus omega squared minus B star k squared E dB into 1 minus P dB over E dA, this thing, and then this is all squared. And then we have to add to that omega squared into E minus P B star minus dA plus dB K squared, and then like that, and then all of this thing squared. So that's the formula. And again, if we want to see when is the condition for pattern formation, so if there are peaks in the power spectrum, that tells you about pattern formation. And the condition for that is EDA is greater than PDB. And so that's the condition. So if you have no noise, to just set the noise equal to 0, then what you have is pattern formation only in the deterministic region, and P is equal to 0 outside of that. So, but if you have noise, then the condition is very mild. And you can get patches that are formed by noise. So you get patches stabilized by noise. And the interesting thing about those patches is that if you look at what the behavior looks like, so if you look at as omega and k go to infinity, what you can see happens is that P of k and omega asymptotically goes as either k to the -4 or omega to the -4. So you have a tail, a power law tail, if you have extrinsic noise. This is extrinsic noise. So what we did here is we just took a continuous density description of the system. We didn't take into account the individuality. We didn't take into account the discreteness, and we just added noise to a reaction diffusion equation and did a computation. Okay, so there's nothing conceptually tricky about that, but we don't care about that. What we actually care about is what happens when we have an individual level model. So now I want to talk about the individual level model for this problem and show you that we get something different. So we're going to do this the same way that we did before in the previous lectures. So what we're going to do is we're going to write down the equations. So the reactions, if you will, that are allowed are the following ones. So we have B goes to B plus B, at some rate B, 2B goes to 3B with some rate E over V, A plus B goes with some predation rate P over V to A plus A. The predator eats the prey and then uses the energy to make baby predators. and then there's the predator competition, which results in a term like this. And then we also have other terms, which I'm not going to write down, to describe particles hopping in space. So you can imagine putting these particles on the lattice and then writing a term that says the particle starts at lattice site I, hops to a neighboring site with some probability, and from that probability you can extract the diffusion coefficient. And I'm not going to go into that, it's conceptually very obvious. And then what we do, so now we've got that, so then conceptually what we would want to do is then we would write down the master equation. So we would have the d by dt of the probability of the system having NA and NB predators and preys at time t, and then we wrote down what that was before. So that will look something like B into minus NB P of NA and B plus various other terms. And I'm not going to write them all down. Okay? So you could do exactly what we did before, but this isn't what we want. The reason it's not what we want is that the number of particles is now the number of particles at a given lattice site. We've got all these particles hopping around on the lattice, so it's not like I want to know how many are there in the whole system. I want to know how many are there at this point in space R. So this thing is now going to be, this is just for the site R. Say on a lattice. And then that means there's going to be plus other terms that describe the probability of hopping into and out of this site R. So now we're going to have a set of coupled master equations, one for every site on a lattice or every point in space, and that's something that's very unpleasant to think about. And so we're going to do something different from that. So you had a quick question, EJ?
So how does individual model provide the AD effect?
How does it provide the ALI effect? It provides the ALI effect through, so you see here there is the coefficient E. Can you see that one? So if you go back to the ALI effect, what is happening in the ALI effect is this term over here. So you have a nonlinear production of prey. So that's how it's included in the model. Okay, so let's so what we're going to do instead. So we don't want an infinite set of master equations for each point in space. These are coupled together, so it'd be even worse. We don't want that because that's awful. So what we're going to do instead is we're going to use a trick from quantum field theory. And this trick was first invented by Massadoy in 1976. So what we're going to do, so let's talk about the basic idea here. So what we're going to do is we're going to set up annihilation and creation operators and then we're going to write the master equation in terms of a Fock space, meaning a set of coupled Hilbert spaces with different particle numbers. So different Hilbert spaces with varying particle numbers. So that's what you do when you do annihilation and creation operators in quantum mechanics. And there's nothing special about quantum mechanics. We can do it in the classical system as well. So let me briefly show you the highlights of how this works. Obviously, you're not going to get it in just this short lecture. You're just going to see, I want you to get just the general idea. The mathematics takes a bit of time to go through, so it's not trivial. So let me just give you a sort of guidepost for it. So we're going to write the state of the system in the following way. I'm going to write it in the following way. I'm going to say, let's have some basis set. And first of all, I'm going to talk about this with systems that don't depend on space. So just NA and NB. So what we're going to do is we have a state of the system represented by a ket, NA and NB. And then the coefficients of that are going to be the thing that we actually want, the probability NA and NB. And then we're going to sum over all possible values of NA and NB, and that's going to give us a vector in this Fock space. So that's the setup. It's different from quantum mechanics. In quantum mechanics, the coefficients of the state vectors, the coefficients of the expansions, that tells you about the probability amplitude. And then to get the probabilities, you take the coefficients and you take the absolute value squared of the coefficient, and that gives you probability. That's the special feature of quantum mechanics. That's Born's rule, which still needs to be explained. Okay, nobody knows where that comes from. That is the fundamental mystery of quantum mechanics. In classical mechanics, we just say that the coefficients are directly proportional to the probabilities. So we don't have entanglement. Okay, so that's the difference. So now we can define annihilation and creation operators. So what I can do is I can say, well, I have an annihilation operator. So A acting on the state Mn. I'm going to just write it as Mn, just to be to make it quicker. That then gives you M acting on the state M minus 1 and N. So it lowers you, and then the creation operator will give you a state with M plus 1, prey. So that looks like this. Actually, predator, I should say. So this is annihilation. This is creation, and this is for the predator. And these operators commute like this. And so I have that's how I increase and decrease the amount of predators in the system. And I can do the same thing for the prey. So I'll use some variables which I'll call C, acting on M and N. And what they do is they go the opposite way around. And this is for the prey. And as you would expect, C and C hat commute like that. If I wanted to do this, you can do this in another way. Another version of this, you can take the operators telling you about particle creation on a lattice site. In this model, the predators and prey, there's many of them allowed to be at any given lattice site. But I could also say, well, I want to define my system to be very, very coarse-grained. So actually, each lattice site can only have one predator and one prey. So these variables only have 0 or 1. In which case, the way you do this is you don't use bosonic operators, you use Grassmann operators. So then you would use fermion operators obeying a Grassmann algebra to create and destroy, because you only have 0 and 1. That's what you get with Grassmann operators, and so you can do it like that too. So that's the basic formalism. So then what do you commute? What you compute is the master equation is a time-dependent equation for the probability. For dp by dt equals blah, blah, blah. We've written it down before. So in this formalism, it turns into d by dt of the state vector psi of t equals some operator L acting on psi of t, like that. And this is, so this operator L, you can think of as being Hamiltonian, but this operator is actually not Hermitian. So I will call this the Liouvillean operator. It's not a Hermitian Hamiltonian. So I'll call it the Liouvillean with a symbol L. And let me give you an example of this. So the example I'm going to use is one from one of the first papers using this method, which was one that I wrote when I was a graduate student, which is a very simple. I used it to solve a problem in crystal growth, but so this example is from JPhys A in 1984. That's when it was eventually published. And so the idea is this: suppose I have a single species. Let's call it A, and it undergoes the reaction Na goes to N prime A. So that's an example of the kind of chemical reactions that we're talking about. All the reactions we're talking about are special cases of that. So then now the question is, what describes the time evolution of the system? Can we write it down? So now the question is, what describes the time evolution operator? So we have to know how to construct it. So you might think, well, that's pretty easy, because you just say, well, L is going to create the N prime of these objects, and it's going to destroy N of them. So it's going to be something like that. So this one, this is meant to be, I guess C, if you like. Well, let's call it C. So you might say take C. So I'm going to destroy N of them and then create N prime, and that way I've taken N of these objects and made N prime of them. So the idea is that this term, this destroys the NA, get destroyed. And I'm going to change my notation. Excuse me. I just realized what I did. So this really is meant to be A. I changed the notation. Well, I didn't change it. I changed it on myself. Okay. A without the hat means destruction. A with a hat means creation. That's how I did it when I wrote these notes. So NA get destroyed and N prime A get created. And so it looks like this is the operator way that you would describe this chemical reaction. It's not correct. Okay, can anybody guess why this is not quite correct? If you take a guess, you'll probably get it right, but you won't be able to demonstrate the guess, because it requires a bit of mathematics to do. When we're writing down a master equation for a probability P, there's a constraint that we need to satisfy. What's that constraint? Probabilities have to sum to 1, yes. So this is not unitary, okay? So this is not correct. It does not conserve probability. Okay, so what does? You can work it out. I'm just going to tell you the answer. So what you have to do is it should be this, k times a hat to the n prime minus a hat to the n times a to the n. So what you have to do is you need to subtract a term that goes like a to the n to the right of any creation operators. And choose the power to conserve probability. So it's not difficult to do this, but you know it would take a while to explain it. So this is just the answer, and so then if you were to say, okay, let's see how do we work it out? Well, you can verify that this gives you a master equation, which looks like this: dp by dt of you know, what is the probability of finding m of these objects m copies of a, that's time t, and that is equal to a master equation which looks like this: m prime w of m prime p of m prime and t minus w of m prime m p of m and t. So this is just the standard form of the master equation, and the w, these transition matrices, w of m and m prime, is just the rate k times a Kronecker delta of m prime plus we are what? Oh, I'm not going to write it down. I think there's a typo in my notes, and I'm not going to write it down. So I will fill that in later. It doesn't matter. We're not going to need it now, but you can calculate it, and it's exactly what you would get if you did this by a standard method. Okay. So all right. So now what I want to show you is, okay, this is fine. But now what happens when you do this with a spatially extended system? So that's the basic idea. So now I want to show you the application to the Levin-Siegel model. So what you have to do is you have to construct the Levilian. So what you get is a Levilian density that looks like this. So I'm just going to write down the formula, for the spatial terms. So I'm going to call this part. This isn't going to be the full L. I'm going to call this part H. So I'm going to define this operator. It's going to be the following. It's going to be B C hat squared minus C hat times C plus E over V. It's the Lie effect. C hat cubed minus C hat squared, C squared plus P over V A hat squared A C minus A hat A C hat C plus D over V 1 minus A hat A squared. So that's what you get. That's just the reaction terms. Okay. Now we still need to add the diffusion. So the way we add the diffusion is we add a bunch of terms, which I'm going to write down in a second. They'll look very obvious to you. They're just the diffusion terms, and then we take this sort of reaction density, integrated over space and time to get an action. I'm going to tell you what is the action. So including the diffusion, that gives us what I'll call an action, which is basically the Liouvillean, but it's going to be now integrated over time and integrated over space. So it's a scalar quantity. So it just looks like this. So it's an integral dt, then integral over space, dimensions d, and then it looks like this: a hat d by dt a plus c hat d by dt c minus d a hat del squared a minus d a c hat del squared c, and then all the other stuff that I just wrote down on the previous page. So that is the action that I claim generates the master equation for a discrete version of the Levin-Siegel model. Okay, so this is fine. This is sort of almost undergraduate or graduate level elementary quantum mechanics, where you have raising and lowering operators, annihilation creation operators. Okay, so what we're actually going to do, if I were to write this down as a path integral, so in path integral terms, and if you don't know what a path integral is, I'm not going to explain it now. So we talked about it a little bit in class, but not a quantum one. So in path integral terms, we can write down a partition function. And in this partition function, these variables, which are operators, become complex numbers. So the reason why people like path integrals, one of the reasons, is that instead of having to deal with operators, you deal with complex numbers instead. So there's a partition function which you can write down, and I'm just going to write it down and not fully define the precise mathematical structure of it. So it's path integrals over the fields, and then e to the minus s. So that's just a formal way to represent the solution of the individual level model, discrete stochastic model here, and this everything here, this is exact. Okay? So it's exact but useless, and now we're going to have to work out how we can do calculations with it. So I want to just make a comment about the connection with quantum mechanics. Again, just to show you what there is, not to explain it in great detail. So if I was doing this in quantum mechanics, the analog of this in quantum mechanics would be the following. I would write down a partition function, which looks like this, the integral of a path integral of the wave function, and then I'd have the action. But now the action goes as e to the I over Planck's constant s, and the action is just the integral over space and over over time and space of the Lagrangian density, and L is the Lagrangian density, which you can write down for a system. For example, it might be something like psi star d by dt plus h bar squared over 2m del squared acting on psi plus psi star v psi. So that would give you, say, this is equivalent to the Schrödinger equation. This will give you the Schrödinger equation of a particle in potential, and the Lagrangian is described by that. All the quantum fluctuations are described by the partition function. And if I wanted to know the classical limit, how do I get the classical limit from this? Is I look at the configurations where the phase factors don't cancel out. So look at this thing here. This is a pure phase. It's a complex number, e to the I something. So it's a pure phase. So this isn't like doing statistical mechanics where you look at the maximum value of the Boltzmann factor. Here now what we're trying to do is, this is a pure phase, so it's basically just a bunch of oscillations. And those oscillations are always going to cancel out unless you're on a trajectory where the phase is stationary. So the configurations where the phase factor don't cancel out, so those are configurations in space and time where the phase is stationary. And so that means that what happens is they're the configurations where ds by d psi star is equal to 0. So if I take that action and make it variational derivative equal to 0, then along the trajectory for psi as a function of x and t, that will then not cancel out. You won't get these cancellations, and that gives you the Lagrange equations of motion. So that then ends up giving you d by dt of dl by d psi dot minus dl by d psi is equal to 0, which is Lagrange's equations of motion. In other words, the classical equations of motion. So so why do we go through this? Well, the reason we care is that in our case, the deterministic equations of motion are the analog of the classical equations of motion. Those deterministic equations of motion also come from saying ds by d psi I equals to 0, where psi I is equal to a hat, c, and c hat. So if I take the action that I've got there, take its variational derivative set it equal to 0, that will give me the deterministic equations, which will end up being actually the equations for the Levin-Siegel model. So this description gives you the Levin-Siegel model, but it also gives you the quantum corrections, but they're not quantum corrections, they're stochastic corrections. Okay, so now I want to just mention a technical point. So how do we do this calculation? So there's a problem. So a hat, c hat, etc. They're not observables. So what we want to do is recast this problem So yeah, so so this is just going to come out of thin air, and but I need to show you this in order to show you how we do the calculation. So what you do is you actually write down new variables, which turn out to look like this. And again, the only way you can do this is to reproduce the calculation that was done in my paper from 15 years ago. Why it has to be like this is not mathematically obvious. It involves the theory of coherent states and so on. So these, so you make this transformation, and what do you get out of it? So these variables, the field z hat and the field rho, these are so-called response fields. And some of you may have, how many people here, I know Chan has run into this. How many of you here have looked at Martin Sigero's formalism in quantum field theory? Maybe nobody, or statistical mechanics. Okay, so these are called response fields in statistical mechanics. They allow you to compute correlation functions. So so z hat and rho are those, and z and rho correspond to the numbers of predator and prey. Okay, so that's what they are. So if I want to, so the reason is this: if I want to compute some function of these variables z and rho in this formalism, where the expectation value is taken with respect to this path integral that I've shown you, that is the same thing in the original formulation of asking what is the expectation value of that same function of the number of predators and the number of prey. Okay, so that's technically how you do that. Okay, so then you can so then what you can do is then you get the Lagrangian density in terms of these variables, and I'm going to just write it down. There's no physical significance, sorry, to this for now. You can see that these are quite long calculations. Class nearly finished. Still hasn't finished. Okay, this is the point where everybody should be taking some more chocolate, okay, to stay awake. Okay, so this is the exact description of this whole problem. Okay, it's exact, and you might say this is a lot of work. who cares about all this stuff, okay? The reason is this, any alternative that you can think of to do this calculation is far worse than this, okay? There's no alternative but to do this. Okay, now that was the hard part. Here's the easy part. The easy part is to do the Van Kampen expansion. So now we're going to do the Van Kampen expansion. And I'm just going to, again, I'm going to just sort of do it very, very sketchily. I'm just going to tell you what the starting point is. So step one is you write Z is equal to Z hat over the square root of V, the volume of the system. Rho hat equals rho hat over the square root of V. So these get replaced by that. And then I write that Z is equal to V A plus the square root of V times some fluctuation. And rho is equal to V B, the average value of the prey, plus the square root of V times a fluctuation. Then I write the Lagrangian density as the square root of V times the leading order term plus an L2 plus a term of order 1 over the square root of V. So this is how you do the Van Kampen expansion. You do an expansion in terms of the square root of the volume. And then what you do is you get the same calculation we did before. You can work out what L1 is. And what you get is, I'll write it down, d by dt of B plus Z hat d by dt of A minus dA Z hat del squared A minus dB rho hat del squared B minus B rho hat minus E B squared rho hat minus P A B Z hat minus rho plus D A squared Z hat. Okay, so why did I bother to write this down? Okay, if you now then look at the mean field equations, so if you write down dL1 by dz is equal to 0 and dL1 by d rho hat is equal to 0, this gives you the deterministic Levin-Siegel model. Okay, so far we did nothing. We just start off with a deterministic theory. We made an individual level model, and then I showed you that the classical limit, the deterministic limit of the individual level model, is the equation that we started off with. You can just check by differentiating that this gives you that. So that's why I wrote down this intermediate step. Okay, so that's not why we do it. We're doing it because we want to do the fluctuations. So now we do the fluctuation correction. So this is step 2, and I'm not going to write them down. You do the fluctuation correction. And then what we're going to do, so you get an equation for L2, and I'm not going to write it down, but it's in the notes. So it's a big mess. Then you say, okay, now I want to write down a Langevin equation that corresponds to this. So how do you do that? Well, I'm going to define the Langevin equation in terms of two new vectors. So the vector x is eta over psi, and the vector y is z hat rho hat. So when I write things down in terms of that, then I find that L2 can be written as y transpose d by dt of x minus y t a x minus 1/2 y transpose b y, and these matrices A is equal to a bunch of stuff, just like the ones that we had before, the ones I showed you back over here. So here I had these matrices A and B, this matrix A over here on the left-hand side. So it's like that, but it involves k-squared, just like this one does. It's just more complicated. Okay, so it's the same idea as what we had over there. And so I'm not going to write it down. So you get this matrix A is equal to that, and this matrix B is equal to something else. And now once I have that, then I can write down the Langevin equation. So I can just use the same result that I just showed you at the beginning of the lecture. Once I have that action, I can write down the Langevin equation. And so my Langevin equation is I omega x is equal to A x plus gamma, and gamma I of k and omega, gamma j, k and omega is equal to the matrix Bij, and then I can solve for x, and then I can calculate the power spectrum. So then I can compute the power spectrum, and I'm not going to tell you the full formula because it's messy. What it looks like is something that goes like over omega to the 6 and k to the 6 divided by something that goes as omega to the 8 over k to the 8. And so what that means is that you get a peak in the power spectrum for the pattern. And the decay of the power spectrum goes like omega to the -2 or k to the -2. So your power spectrum ends up looking something like this. If I just look at it, take a snapshot, like so, it has a peak, and then it has a k to the -2 tail, and this is the pattern. So that's the prediction. And then you want to find out, well, that's great. So when do I get the patterns? And so it turns out that you get the condition, again, just by analogy with what I told you earlier in the lecture, you get a formula that looks like this. There's the formula. And if I plug in the values that I had before for the Turing pattern, so I had B is 1/2, P is equal to 1, D is equal to 1/2, E equal to 1/2. What I get is that D over A over DB has to be greater than 2.5. Previously, we had 28. So what I've just shown you, or just told you, is that that the condition for stochastic pattern formation is much easier to satisfy than deterministic. So let's have a look at the phase diagram. Here we go. So I'm going to take these pictures and stick them over here. So that's the paper. There's the formula. Okay. Yep. So here, what I've shown you is the ratio of the diffusion coefficients on the vertical axis. And here is P over D or something like that. And the point is that classically, or deterministically, I should say, you get deterministic patterns here. Here you get stochastic patterns. And here, just in this little sliver, you get no patterns. So everything above the blue line was the only place where you got Turing patterns. Now everything below the blue line, except for that little sliver, you now get stochastic patterns. They have the patterns have the same wavelength as the formula that you get classically, but you have the same formula, but the pattern itself is random. Okay. Okay, so the wavelength of the pattern is the same formula as deterministically, but the pattern is disordered. Okay, so how do we know that this is really true? So the reason we know it's true is that we did an experiment. Okay, I'm not going to show you the data. I'll just tell you about it. So we did an experiment where we created, using synthetic biology, signaling molecules that diffuse and they're constructed to have the Turing pattern instabilities. The activation and inhibition are produced in a biofilm of E. coli. We could connect them up to fluorescent reporters, and then we simply let the system go, and we put it into a regime. We were able to figure out how to do this. So we put it into a regime where deterministically no patterns could form. And yet we were able to see patterns that formed. They were disordered patterns. We could measure their correlation functions in space and in time, and they had the k to the -2 asymptotic behavior that I just showed you, and they had the wavelength that agrees with what we predicted from the theory. So we know in biological systems where you have discrete numbers of molecules diffusing and undergoing chemical reactions, you can now form patterns, and these patterns are easy to create and have these characteristics. Okay, so that's all a very, very big rush, a huge amount of information there, just showing you how far you can take these ideas of pattern formation into certain types of biological systems that I'm particularly interested in. We also applied this to looking at pattern formation in the visual cortex. In the visual cortex, you can get patterns. Those patterns occur when you hit your brain with a hammer, and then you get a hallucination, and those patterns then stop you from being able to see properly. So then you can ask, what structure of the brain would you have in terms of organizing the neurons in the brain so that the probability of seeing patterns was minimized? Because if you see patterns, then you can't see the visual field. So you want to stop that happening. So when you go and look at it, you work it out, what you find is that the large-scale architecture of the visual cortex, it has a certain thing that you can see experimentally, but when you work out the theory of it, you find that only that particular architecture that you see in experiments will actually suppress hallucinations, enable you to have the biggest chance to be able to have a functioning visual cortex. So I think that evolution actually evolved the visual cortex in primates to minimize these fluctuations that would otherwise prevent regular vision. The last example of this I want to just mention in passing is not to ecology at all, but to fluid mechanics. So about 8 years or so ago, we studied how fluids become turbulent in a pipe, and what we discovered was that when you look at the very close to the threshold of the onset of turbulence, there are modes in the pipe that in the fluid that behave like predator and prey. And then we built a predator and prey ecosystem for those modes. And from that, we were able to then work out the field theory for the laminar turbulence transition and show that it was a particular theory, a stochastic process known as directed percolation. And last year we finished a 7-year set of experiments and analysis, and we verified this prediction experimentally in pipe flow. So these techniques are sort of like, from my point of view, the cutting edge of these areas of biology and even fluid mechanics, other areas where stochasticity and individuality and discreteness are important. Okay, so that's the end of this course. We're going to meet again next week when the students have taken the class, and hopefully some of the rest of you who are observers of the class will have a chance to present some papers, or term papers. I hope you enjoyed the class. I hope you found the homework interesting. I hope you found the lectures stimulating. I hope you enjoyed each other's company, and I hope that this class will have affected something of your outlook about what emergence means. So thank you very much. Okay. So see you next week for the final exam term paper presentations. And thanks for being here. Okay.